Good afternoon, and welcome to hand-wavy chemistry, where we do not delight in the details, but rather bask in the big picture. Today, I want to talk to you about Markovnikov's rule. I really enjoy Markovnikov's rule, because when you ask a chemist what it is, they give you the beautifully hand-wavy response of the rich get richer, rather than the drier, more formal reply of during the addition of a protic acid or other suitable polar molecule across an asymmetrical alkene, the proton goes to the carbon atom that has the most hydrogen attached to it before the addition began. But what does that mean? Let's start with the simplest asymmetrical alkene, propene. And let's add hydrogen bromide, HBr, to it. There are two possible orientations that the HBr could add across the double bond. We could either end up with the bromine in the middle and the new hydrogen on the terminal carbon, or the new hydrogen could go in the middle and the bromine could go onto the terminal carbon. Now, everything in chemistry happens due to a mixture of steric and electronic effects. Steric means size, shape. Bromine is a much larger atom than hydrogen. So in this case, if we were expecting steric control, that is for size to be the most important factor, we would expect the bromine to go on the terminal carbon because it is less crowded. It's easier for it to get there. But that's not actually what we see. We see that the bromine goes onto that middle carbon. Even if we add more steric hindrance, for example, if we had methylpropene, the bromine still goes on to that middle carbon. So what's happening here must be driven by an electronic effect. Double bonds are regions of electron density. And when we are talking about the drier definition of Markovnikov's rule, we talked about a protic acid, which means that we can think of that hydrogen bromide as being H plus and Br minus. Well, the double bond is a region of electron density, so it's not going to be of much interest to the Br minus because it's also negatively charged. But that H plus, now that will be attracted to those electrons. And there are two ways that that double bond can break and bind to the proton. It could either swing this way or could swing down that way. And regardless of which way that double bond breaks, we end up with a carbocation, a positive charge on a carbon atom. Carbocations are not stable. They look to readily react. So the Br minus being around is a good thing because it will be able to complete the reaction. However, let's think about the stability of the two possible intermediates where we have our carbocations. Could either be on the central carbon or the terminal carbon. This is a positive charge. We can stabilize it with electron density. Protons only have one electron, so don't contribute much to the electron density around the molecule. Meanwhile, carbon atoms have 6 electrons, much more electron density. So having the carbocation surrounded by as many non-hydrogen atoms as possible will help stabilize it, as those additional electrons will help lessen how much of a positive charge that carbon feels. Because of this, that central carbocation is much more stable than the terminal one. And if we were to consider that methylpropene, its carbocation, if it's on the center, is fully surrounded by carbon atoms. There's no hydrogen there. So it makes it much more stable. And indeed, when we add HBr across the double bond of methylpropene, the only product we see is with the bromine in the center and the additional hydrogen going on the terminal carbon. So why do chemists just say the rich get richer? Well, let's put it this way. The hydrogen-rich carbon gets more hydrogen-rich. So that hydrogen-rich atom gets richer. Makes it very easy to remember this rule. This idea that the products are determined by the stability of the intermediates is seen all throughout organic chemistry, and is why different substituents attached to a benzene ring can be orthoparadirecting or metadirecting, depending on how it is they can distribute different charges around that ring. The haloalkanes formed by this type of addition are important because they provide a place for more chemistry to occur. Alkanes are usually very unreactive, but a haloalkane can react where that halogen is attached. But Markovnikov addition keeps putting it on the more substituted carbon. But what if we wanted the halogen on the less substituted carbon, that terminal one, for example? Well, luckily for chemists, there are anti-Markovnikov reaction pathways that avoid the formation of a carbocation, for example, free radicals. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.